Okay, good afternoon, everyone. Welcome to our monthly machine learning presentations of the AMMnet machine learning group. Today, we are having a very important topic to be presented by a prolific researcher. Is in person of Professor Dennis Murithi. He's going to present on malaria risk prediction using AI models. Professor Dennis K. Murithi is an associate professor, statistician, and lead data scientist at the Center for Data Analytics and Modeling in the Faculty of Science and Technology of Chuka University in Kenya. A dedicated educator, researcher, and is a recognized expert in the field of statistics with over 15 years working experience. His commitment lies in advancing scientific knowledge, mentoring future scientists, and promoting interdisciplinary research globally. Professor Murithi's work primarily focuses on applied statistics, data analytics, machine learning, and artificial intelligence with applications in healthcare, agriculture, education, and business. He collaborates with both academia and industry partners to tackle real-world challenges using statistical tools. He has published many articles in internationally referred journals and is a recipient of research grants awards. He's a statistical modeler, enthusiastic, certified public accountant, and a member of the global AMMnet and the International Biometric Society. So today, we are going to listen to his presentation on malaria risk prediction using AI models with practical R sessions. So let's have Prof now. Please, over to you, Prof.
Thank you, Prof, for the introduction. Is my presentation visible from your side? Hello?
MC, go ahead.
Is it visible? Yeah, okay, thank you. So welcome. I want to welcome each one of you to today's presentation under the title Malaria Risk Prediction using AI and machine learning models in R. We will explore building interpretable AI and ML model for malaria risk prediction and analysis in R. The focus is on current interpretable machine learning model packages and also the DALEX, which is a very nice package for model interpretability. The objective is to develop interpretable machine learning model for malaria risk prediction. This is intended to improve early detection and intervention strategies. Utilizing R for transparent and explainable predictive modeling. Why is focus on malaria? Here I have some global statistics from World Health Organization report of 2024, where they reported that globally in 2023, there were an estimated 263 million malaria cases and 597,000 malaria deaths in 83 countries. World Health Organization indicated that Africa region carries the higher share of the global malaria burden. That in 2023, Africa region was home to 94% malaria cases, accounting for 246 million, and 95% accounting for 569,000 of malaria deaths. Further, children under 5 accounted for about 76% of all malaria deaths in Africa region. In my presentation, I want to explore the complex interaction between patient level factors, environmental factors, and parasite information. In terms of patient level data, I'll look at the age of a patient or an individual, gender, primary clinical symptoms such as fever, headache, nausea, and others. And then the medical history of the individual. Environmental factors, I'm looking at the temperature, rainfall, endemic zones, and also humidity. Endemic zones, in terms of malaria study in Kenya, Kenya is divided into 5 endemic zones, and we look at them. That's why environmental aspect is very key in terms of zones. Parasite information, I'll look at mosquito density, the number of mosquito counts per square kilometer, and also the type of malaria parasites. Here, I'm looking at Vastalam. We have VVAX and other two we'll also see in the dataset. The target variable is malaria test results, which is a binary classification variable with positive and negative categories. The importance of interpretability in malaria risk prediction, one is to build transparency and trust among stakeholders, such as healthcare professionals and policy makers, are more likely to adopt models they understand. And two, help identify which features are most influential for a given prediction, aiding in trust and transparency of the model. Another importance is model validation. It ensures that predictions align with the domain knowledge. The other one is actionable insights. It helps identify key factors driving malaria spread and outcome, such as climate conditions or patient demographics. The procedure that I want to adopt for this particular presentation is where I'll prepare the malaria data set. Before training the models, we will ensure our data is clean and well prepared. When I talk about clean data, it's ensuring that there are no outliers, and if they are there, we give them justice. We look at the missing values. If there are variables that require transformation, it is done at this stage. Then after that, we go to the next step of training the machine learning model. In my presentation, I'm looking at training a random forest decision tree. And if time allows, we also look at the ingredient boosting model. All these are models available in current package. Then the other important step will be model interpretability techniques in DLAX. DLAX is a very powerful package used for model interpretability. The key features of DLAX, that's why I'm concentrating on this package. One is features importance. Kindly unmute. Thank you. Key features of DLAX. One is feature importance using interpretable machine learning. This it quantifies how much each feature contributes to the model prediction, and also identify most critical predictors of the malaria risk. Another feature is breakdown predictions. It provides local explanation by decomposing a prediction into contributions of individual features similar to sharp value model. Another one is local interpretable model, agonistic explanation. DAREX works with any machine learning model, including those from carrots and also the Tinde models. It focuses on explaining individual predictions and generates the plots to illustrate feature contributions. A good example is explaining why a specific patient was classified as high risk. Another important feature is partial dependence plot. It visualizes how changes in the feature affect model prediction, and also understand the relationship between features and predictions. A summary of what I've said about the key features of the DLAX is model explanation, as I've said, breakdown prediction into understandable components. Feature importance identifies the most influential features. Remember, datasets are several features. We want to see among them which is more responsible for positive malaria instances. We have sharp and limb support. It provides individual predictions, explanations, and model comparisons where multiple models on the same dataset are compared. So allow me to shift to R and demonstrate how to build these models using malaria dataset. So this is R Studio. I prefer working with R Markdown because R Markdown is a powerful tool in R for creating dynamic reports that combines count, outputs, visuals, text in a single document. You'll be able to see the count and the outputs and adjacent to each other. How do we access R Markdown? You go to File, then a New File, and then you navigate to R Markdown. If you click R Markdown, you'll be able to see this window where you put the title. As you can see on my slide, there is title, Malaria Risk Prediction using AI and machine learning models in R. You put the title, then your name, and of course you choose HTML and then say okay. You'll end up with an interface like this one for building the model. Now, I have done my presentation. Let me go straight to the first step when you want to build these models. The first thing is you install and launch necessary packages and libraries that are needed for this particular model development. The most important model, I can write a few. One of them is library ggplot. Library ggplot. We need this library for data visualization. There will be quite a number of issues that we need to see in this particular demonstration. I also need the library TikTok. This is for determining the time taken for a model to learn. Some models take long, so it's important to time. How long will it take for this model to be trained? I will also consider the carrot. This is a package or library that contains machine learning models for training purpose. So any model that I need, for this case, I'll use the I'll train random forest, the decision tree, and also gradient boost. These models are in this particular package. Another important package is this one. We are calling it Deluxe. Deluxe is a powerful tool for interpreting machine learning model. It provides a unified framework for creating model interpretations, making it easier to understand both global and local behavior of machine model. Deluxe stands for Descriptive Machine Learning Explanation. Once you have installed and loaded your packages, the next step is to create a working directory. A working directory is a folder, let me call it a folder, or a directory where your data, your count, and output are located. You can trace them to that particular folder. How do we create a working directory? There are many ways, but I want to show you my shortcut. What you need is go to File, then choose the file that you have created under Document section on your machine. Document section. So if you go to my documents, you'll find a folder, I'm calling it webinar. So once webinar appears here, you click on this. This is a file that contains what I'm presenting here, including the data. You can see I have my data here. I have my R code here. So I want to create a working directory. What you do is you click on this tool, we call it a gear tool. Another window will appear, then select set a working directory. When you click this, a working directory will appear here. You can see on my console here, you can see I have this set working directory. Then you copy. Once you copy this, you paste here on this chunk, and this will be a working directory. This will be, once you copy, this will be the link between your data and R code. How do you put this chunk? Maybe it's good to explain that. There are many ways. You can go to font, then insert chunk. Or you can do it manually. You click, you press this button on your keyboard, Control plus I, the three of them simultaneously, and you'll be able to get the chunk. Then you paste your copied link to connect all your document there. So once you have set the working directory, the next thing is load the necessary data. For the purpose of this demonstration, I'm using synthetic data that I've generated with basic information about study of malaria in Kenya. So this is the data. I'll just write the link data link.csv because mine is a CSV file, as you can see in my folder here. This is a CSV file, and it will be able to load the data automatically. Then once I load the data, I can be able to view the data. Just write view the data to be able to be familiar with the data that you are working with. I hope you can be able to see my data. This is the data that I'll be using. It has all these variables. It has age of a patient or individual. It has gender, rainfall, average rainfall received in that particular area where this patient came from. Endemic zones. These are the endemic zones I talked about. We have low risk, the coastal, and others. So including the target variable, which is malaria results, whether somebody was found to be negative or positive. The other information is on primary clinical symptoms, fever, headache, nausea, all this, and also the parasite information. We have Aspartam, the FIFAX, and others. Then once you have loaded the data and you have seen your data is working, so allow me to learn this. How do you learn this? You just click on this icon here. You'll be able to learn that particular chunk. You can do the same on the data. After that, you do EDA, exploratory data analysis. This is where you look at the structure of the data. For instance, you want to see the structure of the data, I can click. This is the structure of the data. These are the variables that I have in the data set. How many data points? I have 1,000 observations or data points with 18 variables. All of the variables, including the target variable, they are 18. If you look at rainfall, this is a numerical variable. Malaria data is a character variable, and all others, you can be able to get information about the data the information about the data set. The other thing is the names. If you want to see these names, we may require them somewhere. You just write name, as you can see, name data. This is to see the names as they appear in your data set. These are the names that are there in my data set. Each one of them represents a feature in my data set. You can also check whether they are, you want to see whether they are, this one is for removing missing values. That is, if they are there. If they are there, you can check so that you remove the missing values. And then if you want to see the first 5 rows or data points in your data set, you just write end, then the name of the data set. Mine, I will use set data throughout, and I want to see the first 5. If I want the first 3, you just change the number and it will show you the first 3 data points. So this is the information relating to the data set that I'm going to use. If you want to see it in a Zoom point of view, there is this icon here. If you click this icon here, you'll be able to see, to magnify the data, be able to see the data in a wider interface for you to be able to explore the kind of the data that you are dealing with. Once you have done ADA, the next thing is to visualize the target variable. The target variable in this case, I sent in my data set it is here, malaria results, whether individual was found to be negative or positive. In this particular case, the data, then the $, malaria results, I will be able to convert my target variable as a factor. This is very important. We convert the target variable as a factor, and I have it there. Then I want to plot the target variable using ggplot function. And in this case, I also want the percentage to appear on top of each bar. So I've done small modification here. I created a new data frame where malaria results is binary, negative, and positive. I only know from this table, if you write table, maybe X, can try. If you write maybe W, equal to table this, then I print W, you will be able to see how many, this is $. You will be able to see How many cases? How many cases or instances are positive and how many are negative? So from this data, you can see 820 individuals were found to be negative and only 180 were found to be positive. Then you convert, you compute percentage. You compute percentage. I've done it here. The same from the same data point. You chain with this one. Then this is mutating. We say you mutate, that is transforming or computing a new variable. In this case, it's percentage, it is there. Then I will plot. The most important is I'm using the DT. This is the data frame that I'm using in this case. Then the X variable is malaria results. This is the most important thing. And I want a bar chart, and I'll be able to get these results here. So why do we do data visualization? You want to check whether the data that you are working with is balanced or imbalanced. So if you look at this chart, automatically what we have here is imbalanced data, where minority instances are the positive cases and majority are people without this disease, or they are not affected with this disease. After visualizing, so we have seen when the data is imbalanced, we can't train a model with imbalanced data. Okay, we can, but we may end up with biased, or what we call overfitting, because in this particular instance, is a case whereby if you're in a room with a group of 20 people, you ask 15 people maybe to sit on one corner, and another group of 5 people, another corner. Then when a new person enters that room and asks that person to join any of the two groups, you may find that the new person may tend to associate him or herself with the majority. So already there is bias. So there is a way we will treat this data in such a way that will ensure that there is no biasness when the model trained is classifying the instances. I was also to check for the zero variance. This is how you check whether there is features with little or no variation. This is the count. If I run this count, you will find that there is no a single feature which has no variation or little variation to the target variable. All of them are considered to have what? Impact on the target variable, which is malaria result outcome. Once you have done all that, the next thing is partitioning the data set into training and test, training set and test set. And I'll use this function, we call it create data partition, which is found in current library. And with this, you will be able to partition your data. In this case, I want 75% of the observation to be the training set, and the remaining 25% to follow under test set. What do I mean by training and testing? If I have 100 observations, I will use 75 of those observations to train my model. It's like building a model to train my model. Then I will check whether the model is performing well by using the remaining 25%, which was not used in training the model, to counter check the performance of the model. So this is the function I'm using. Then this is the count. I want 75 to be the training. I can even use 8 here and maybe 20 or 70 and 30. But in this case, I've decided to use 75 and then use 25% for testing. If you learn this count, it will give you dimension for each set. I end 1,000 data points. If I split into 75% for training, 750 observations will follow in training set and 250 in the test set. Number of variables remains the same, 18 for the two sets of the data. The next thing is to fill the models in the carrets. This is also important to be able to know which model you are going to use. If I run this code, model equals get model information, then the model names, you'll be able to see the carrets package has over 200 239, yeah, there are 239 models. All these models are machine learning models that are used in both classification and prediction. So these models, you choose the one that you want. For my case, I want to use random forest. So for the random forest, I know I have RF to stand for random forest. I think it's among them. We also have others like for the decision tree. We will see them. And there is also the other one, which is XGBoost. They are here. So you just choose the model that you want to do and give a reason why you want to use that model. Before I train the model, it's also important to do what we call resampling of the data set. The importance of resampling is to ensure the data that you are using to train the model is balanced. Remember, we had imbalanced data. If you allow me to go back a little bit, this is imbalanced data. So if you train a model with this one, there will be element of biasness when you are using that model to do the prediction. The most important thing is you ensure the data is balanced. And to ensure the data is balanced, I tried 3 methods. One of them is undersampling, oversampling, and hybrid sampling. And the 3 of them, it is oversampling that gave me good results, which to me, I think it is the best procedure, because if you have small data set, if you do undersampling, you reduce it further. So it even, and you know, machine learning are trained with big data, with large amount of data. So if you reduce that data, it even make it so simple, such that it may end up being overfitting on your results. So the best one is you try to raise the minority category, which are positive cases, from 180 to a point whereby they are almost the same as the majority cases. So you can see the sample size has increased for this particular case, so that we have a balanced data. Once you have this balanced data, you are sure of getting a slightly much more accurate model. So the count for this, I have it here. So when I'm training, I'll use now this data I'm calling over. This is the function I'm using. My target is the target variable is this malaria results, and I'm working on I'm only working not the own data set, but the training set only, and the method is over, and it is giving me the results as you can see on the screen. Then from there, there's what we call cross validation technique, very important. Here, I'm considering repeated CV, repeated 5 times with 10 forums. 10 forums. Yes, then such is random. If you tune this, it's very important for the model. So the first model that I want to train is random forest. Why random forest? In this case, because there are so many classification models, is an example learning method that combine multiple decision tree to improve prediction accuracy and reduce variance. It has a parameter, we call it metric, that controls the number of features randomly chosen as candidates for splitting a node in each tree. So I want to train a random forest model. This model is found in library we call carrots. I'm also setting my scent. This is set the scent. This is a reproducibility number to ensure that anytime I run this code, the results remain consistent. They don't change. They remain consistent. Then there is green. We call it the green search for random forest. Expanding the metric, I have this chosen 2, 4, 6, 8, 12. But you can use any other, maybe 2, 3, 6 like that. But I've chosen this. Then I'm also timing. How long will it take for this model to learn? This is, you start by timing, tick. Then you end with the talk. It will tell you how long it has taken to train this model. The function for training random forest, we have this function we call train. This is not train data, it is train function, where I have factor, in this case is malaria results. Then data is over. I'm using the balanced data. Then the method from the model's information, I have RF for random forest. We have the control here. I have done the control above, and then tune green, it's here. So if you learn this count, you can see and learn it, and it took 211.45 seconds to train this model. Let me not learn because it will take close to 4 or 5 minutes. So these are the results. Once you learn this model, these are the results, as you can see. The sample size right now, it has 1,222. It has 17 predictors because one of them was a target variable. So target variable is not there. And then the target variable, it has two classes. It has negative and positive instances. I talked about the sampling. We have 10 folds, each of size, you can see 1099, 1099, like that. Then the results for the model, you can see the best results is when the metric, the parameter in the random forest is 4. I set this 2, 4, 6, 8, 12. If you look at what I put here, is 2, 4, 6, 8. So I wanted to see at this range, which one gives us the best accuracy, and in this case, it's at 4. Yes, with 99 point, let's say approximate 0.3 accuracy. That means these are good results. Then, after training the model, the next important thing is make prediction using the test data set. And in this case, I'm using this function predict. I have my model here, as you can see. And then the data that I'm using is now not training, but test data set. I divided my data set into two, the training and test set. So I use the test set to predict my model. So I'll do that. Then after that, we evaluate the model performance. So this, I'm computing. I'm using the function for what we call confusion matrix, using the prediction function, it is here. As a factor, the data set is test, the variable is malaria test, and then I'm interested with the positive instances only, or the positive classes. So the positive case here, it is the results that I'm interested with. In this case, I'm interested with the positive cases. Then when you say model everything, it will give you the 11 model parametric measures. So it will give you the 11 of them. So if I run this one will not take a lot of time. I'll be able to see the performance of my random forest model. Look at the confusion matrix. 202 observations were known to be negative and predicted as positive. None of the case that was negative but predicted positive. So if you look at this matrix, we have the main diagonal where we have 202 and 45. 45 cases were known to be positive and predicted as positive. There was no misclassification on negative instances. There was no any misclassification. All the negative cases were correctly predicted. But we had negative cases that were predicted as positive. Next is accuracy. You can see the model accuracy. We have 98.8%. We have sensitivity of 1. We have specificity of 0.98. These are good results. And my interest is a positive class. After evaluating the model metrics, the next thing is you try to visualize the important features in the model. There are two ways. You can use the ggplot to see the features that are considered more influential in terms of predicting positive cases of malaria. So I have this code, I have this code. You can see the difference between this and this one. So if I run my results, you will see that when I use the first code, this VIP, like that, as you can see the model, it's giving me these models where if nausea is yes, it has high likelihood of influencing prediction of positive case of malaria. If there is presence of Aspergillus parasites, yes means it is present. Again, it increases the likelihood of individual being found with malaria. The same case for symptom like if fatigue is yes, if ovale, which is a type of malaria parasite is found, again it increases. So it gives you in that order such that you can be able to see which factors are more influential in explaining or predicting instances of positive malaria cases. The one I plotted using the ggplot, we have it here. This is ggplot. It's almost the same, but this one has more expanded. Here is from the one to VIP. From the one to VIP. It's only I write the most important features. But for ggplot, it will give you almost all the 18 features if they have influence, irrespective of how important, how small the important age in the model. So you can see even the order. So even the age, depending with the age, can influence the likelihood of predicting malaria. Then once we have done that, the next thing is preparing data for explanation. And in this case, we want to understand the feature importance, evaluating the model performance, and explaining individual predictions. I'll use the Deluxe package or library. So you can see, create a binary target variable. In this case, I'm now reverting my target variable into from I think it was a factor, into these categories where 1 if it is a positive case and 0 if it's a negative case. Then create the explainer. I've created the explainer here. This function called explain is found in this particular library. And I'm able to create an explainer. Here it is explainer. I've reporting this explainer. This is for random forest. If I have for decision tree, I'll report it as decision tree explainer. I'm also making sure that the target variable is excluded in my explainer. So I'm making sure this variable is excluded. So you exclude and then include the vector which you have converted here. That's why I have this. I have trained malaria result 1 because this is the one that I've already created here. If I run this, it will give me the results, but I'm just creating. The most important thing is the next step. The next step is we talked about feature importance, understanding the feature importance. In this case, I have feature importance, then the model part. Again, this function is found in Deluxe. I want an explanation here, so I'll plot the features. You can even learn the features here. You can also learn the features and see the results. If you run the features here, you'll be able to see the results. Let's see model parts. Explainer, don't take long.
I have to understand.
Yes, these are the results. You can be able to see the explanation. You can be able to see explanation for the feature importance here. All this for each and every every variable in the model. Then the same, you can give a plot to show the same. Still, nausea, the presence of this symptom we are calling nausea as the highest or is the most influential feature in predicting positive malaria cases, and others are in the same order as you can see. Next is explaining individual predictions. Here is where you want this model to explain individual person. I can ask for view. Let me view this. I want to show you how to do this. I want to view the data that I want to explain for an individual. Sorry. Let me view the data. I want to view that data. Yes, this is the data that I want my model to explain, to tell me whether this individual is positive for malaria or not. In most cases, what I'm interested in is the probability or likelihood that this person is positive. I'll look at the age of this person, the gender, all these factors, including the primary clinical symptoms here. Can you see he has not any symptoms, but this particular parasite is present, this and this. So I want to see in such a case, how is the prediction for positive case, and then you do the plots. So if I run this, I hope you can see I'm using the test. It's important to note that I'm using the test set. You can use the test or a new data. If there's new data, this is a person who has presented himself in the testing center or in an hospital. The information is corrected, then that information is fed in a model. And here I'm excluding, because I'm using test data, I'm excluding the malaria variable. This is a target variable, so it should not be there. That's why I have this function, as you can see. So if you plot, you can be able to see that for this individual, the probability or the likelihood is found to have malaria is 15%. I hope you can see here, it is 15%. Let me see whether I can magnify this. Yes, the probability that this individual has the disease or is infected is 15%. And this percent is contributed by, let me start with the intercept. When all these are not present, the probability or the likelihood of this person to be sick is 0.203. When he has no nausea, the symptoms is not present. Can you see it reduces the presence of being positive? But when Plasmodium, which is the parasite, the most notorious parasite, which is considered as the cause of many malaria deaths worldwide, if it is present, it increases the likelihood of this person to have malaria. If again this parasite or virus is also present, it also increases. So you can be able to see if he has fatigue, you can see it increases the likelihood of this person being found with the disease with a positive value of 0.09. If all others, like endemic, this person has no endemic, he has no muscle X, no chill, no fever, you can see it reduces the likelihood of this person being found with the disease. This is one person. We can try another person in the data set because this data set has many, let's put number 10. The test set has 250 observations. We can try number 10 and see the results. If you do number 10, let's see, you can see number 10. So this model, our next plan is to have this model once trained in an app whereby people can be able even to test themselves. As long you can be able to put this information in an app, automatically it will be able to give you the results, whether you are likely to be positive or negative. Let me try number 1 and see. This is patient number 1. Yes, this is number 1. Look at the likelihood of number 1 being found to have the disease, like that. So this is it's an idea that can be able to individualize which factor are responsible for individual positive malaria outcome. In this case, we can see if this person is found to have malaria, this particular feature is highly considered to be the most responsible for the prediction. Next thing is a sharp explanation. As I said, again, I'm also using explainer which I developed and the new observation. You can be able to see the results. Sharp values. This is also a model. You can be able to plot this and see whether there is what could be the contribution of these features towards the predicted case. It won't take long. Let's give it time. Yes, you can see. If there is no endemic, he has no fatigue, he has no, there is no presence of this parasite, he has no fever, it reduces the likelihood of this person to be found to be on the positive side of malaria cases. But where there is, these values are yes. That's why I wanted to try with a case where it could be yes. Maybe I can try with 100. Let's see whether you can 100 and see. Yes, this is patient or individual number 100 in my data set. In my data set, it's 200, the test data set is 250. So I'm trying to predict the results of 100 observation on data point. And this is what I'm getting. Can you see? When he has nausea, these parasites are present. He has all that. It increases the likelihood of this person to be found to have malaria to 62%. So we maybe it's important to mention that when we find this person could be having malaria, we are not certainly say that this person has malaria. What we do is to recommend this person to visit a health center for diagnosis and treatment. But in places where, like remote areas, where there are limited resources, there are no medical supplies, the kits, this model can be used to ensure that only the few resources that are there are used on the most severe cases. So you can see in the presence, if somebody has all this or the parasites are present, you can be able to see that it increases the likelihood of somebody being found with malaria. If you run this the same, the information will be reflected the same. You'll be able to see which features are responsible for malaria cases. Let's give it time. This data, remember, I'm saying this, the next step is developing a model, an app, we call it an AI framework, that if patient can feed this data, automatically you'll be able to know from where you are, whether you are positive or negative for malaria. Then, so you can see, using the SHARP and the model, the results are very clear. There is high chance of this predicting positive malaria outcome. I also have the partial dependence plot. Is a last part of a model explainability, or the features of a deluxe package. If you look at this, maybe if you allow me to reduce the height to maybe 4 to give it time, yes, you can be able to see that how the effect of rainfall according to this data, this is according to this data, and I said this is synthetic data. The average prediction increases sharply when the rainfall increases to around 130, around there. But as rainfall continues to increase, the model average prediction decreases. I don't know. I think this is the importance of having a collaboration with the people working in an environment to tell us what happens, why is the chances of the likelihood of somebody found with the malaria decreases when there is a lot of rainfall in that particular area. Maybe those can help us explain this. If you look at on temperature, again, look at the temperature. Places where the temperature is below, when the temperature is, let's say, slightly 20, the average prediction is high, but decreases as temperature increases up to a certain level. Beyond maybe that 2 degrees Celsius, the prediction average goes up for this particular model. So with high temperatures, we expect chances of model being accurate in terms of predicting positive cases. If you look at mosquito count, let me look at the mosquito count. Mosquito count, these are the number of mosquito in square kilometer, and these are for the individual. So you count the one, if there's a mosquito bite, you count that one mosquito. Another one, and we are assuming these people are within that particular 1 kilometer square meter. So look at as the prediction goes up. Again, this one is, we can work with experts. To me, it's not about how many mosquito bites or counts that were found, but if you come across these notorious mosquito spikes, just one bite, I think, is enough to increase the likelihood of you being found with malaria. So the same steps can be followed for other models, like decision tree models. The same way, you look at these results. I'm training the model, and because this model takes very short time, this one, it takes very short time to train a decision tree. You can see the results. This is we call it confusion matrix. You can see it has an accuracy level of 92%. And then the features importance, if we do this, you can be able to see. So here I've done everything, including prediction. You train the model, you predict, and evaluate the performance of the model, all of them. Then features important, as you can see. According to this model, presence of FIFAX was considered. Presence of FIFAX was considered to be the most influential feature in terms of predicting positive malaria cases. Then deluxe, you do again, you create the binary variable and create an explainer. I'm calling explainer 2. You do the same. Then look at the features. I think if you look at the features, you'll see how the things are. The good thing with R Markdown, you can be able to see the count and the results and adjacent to each other. Then you look at the explainer for individual person. So if you try, you can be able to see. These are what we are saying breakdown. It's able to tell you, yes, all these features and the model, but which one is likely going to influence positive outcome on this particular disease. And I think I'll end it there and ask moderator to take over, and I will respond to maybe 1 or 2 questions if there is any clarification that is needed. Back to you, Professor.
Thank you so much, Prof. This is great. It's a great lecture. Let's appreciate him. Thank you for this insightful lecture. Please, are there questions? You want to take 1 or 2 questions? Questions?